the first time you called me late. Loved you for your wits and your wicked games. Yeah, always on my mind, always in my brain. Yeah, with you the summer came and went in a day, and I've been craving you since the first time that I sat by your side. And I've been on my knees thinking time is gonna fix me inside. No, nothing's gonna make me forget, and I don't think I want to forget anyway, yeah, yeah. No, nothing's gonna make me forget, yeah, I don't think I want to forget anyway, yeah, yeah. I can feel you near when you're miles away, yeah. You can make it shine when the whole world rains. Always on my mind, always in my brain. With you the days are long and the nights are late, and I've been craving you since the first time that I sat by your side. Ooh, and I've been on my knees thinking time is gonna fix me inside. No, nothing's gonna make me forget, and I don't think I want to forget anyway, yeah, yeah. No, nothing's gonna make me forget, and I don't think I want to forget anyway, yeah, yeah. Make me forget, and I don't think I want to forget anyway, yeah, yeah. No, nothing's gonna make me forget, yeah, I don't think I want to forget anyway, yeah, yeah.
Okay, it's Wednesday. Road Rally Race! Full-time streamer now, innit? Alright? Welcome in, welcome in. How you doing? It's Wednesday. Yeah, we're getting back to it. We're getting back to the regular streams. Streaming on Twitch and YouTube. So, yeah, I'm trying to maximize my the platform exposure. Tonight we're going to be working on the final live stream in a series where I have been developing a circuit board for 12-volt controllers. A smart controller that can integrate with Home Assistant and automate my lighting control systems, but could potentially be used for other things as well. You thought yesterday about a light while I was welding? You had a thought yesterday about a light. Context, Road Rally Race. Give me some context on that. So I have been busy since Monday's live stream. You thinking about fitting a ring light around a welder? Is that to illuminate the situation? Oh, I gotcha. That's funny. So the bit of research that I've been doing on my circuit, I've found a bit of a flaw. In fact, I found a couple of flaws in the circuit, and let's go over those right now. Okay, so I have designed this circuit board with a PCB mounted jack in mind. One of these. As he drops it, can he find it? Oh, yes. Right. So one of these PCB mounted jacks, and there's a couple of issues with this PCB mounted jack. The first of which is that I believe this is only rated to 1 amp. The lights that I'm using are 2 amps. So what I decided to do is to go for this wired jack. This is rated for 3 amps, as it is with the wiring that I've got here. All right, so this is rated for 3 amps. More than enough for my use case. However, these MOSFETs that I've got, I believe, are rated up to 30 amps. So if I put this circuit board on sale, I need to make sure that the outputs can manage the amount of current that we're expecting to draw off of these. So I'm going to limit the circuit to 2 amp per channel. And then it's down to the user to apply the appropriate jack in order to get the voltage into the circuit, right? So with that in mind, what I've done, I've updated the circuit. So I've changed it to a 2-pin jack from the PCB mount, and we're going to have to play with the trace width in order to cover that off. But bringing us to the second problem. The second problem, I'm glad I checked, right? So I tried to plug in the connector for the power supply into this jack, and it doesn't fit. The center pin appears to be too thick for the plug that the power supply has. So by attempting to use that, we would have come a cropper, meaning that I would have had to cut the connector off and solder a new jack end on, which is not a major problem, but it's a step that I don't particularly want to go through. So if you can fix the problem source, further downstream, it becomes easier. So Road Rally Race, how are you doing? How is your day treating you? I hope you are well. So we're going to work on the PCB tonight. This is the climax of the series of live streams. So live stream number 1, we did the prototyping on some breadboard to get the circuit working, put the firmware on the chip that we're going to use, and then we made sure that we got the switching, all of that sort of cool stuff sorted. Live stream number 2, which was on Monday this week, we did the circuit schematic, or the circuit diagram, which is this lovely drawing just here, right? Dave wrapping, soldering, big boy soldering. Oh, big boy soldering with the welder. All right, I gotcha. So tonight we're going to do the PCB layup, and we're going to get it to the point where we can output our files in KiCad. And yeah, we're going to be making this. So that after this live stream, the next video that will come out about this particular circuit board is going to be a produced piece of content, which will walk users through each of the stages of this process. And I will link in that produced piece of content back to each of the long form streams. So if people want to kind of do a deeper dive and see how that's done, then that's available. Right, so let's shall we indulge? Yes, I think we shall. So I'm going to jump straight into KiCad board editor, and let's if anyone's got any questions, or if you just want to chit chat as I work, feel free to sound off in the comments. So before we get too deep into today's project, I want to give a big shout out to PCBX. PCBX is sponsoring this project. I'm going to have PCBX manufacture 5 circuit boards so I can do the final assembly and testing before we get to a point where we can get this product loaded up onto my website. So PCBX is a circuit board manufacturing company, and they have a quite unique selling point for new makers in that you don't need software to design your circuit boards. You can use their interactive EDA software, web-based, whereby you can do your own circuit diagrams or schematics, transfer those into board layups, view the files in 3D, and then place an order directly from the website. So if you're watching this on replay, click the link in the description below. But yeah, PCBX.com, I believe, is the address. I'll make sure the link in the description is correct. If you're watching on Twitch, if you go to my About section, you will see a panel there with a link to PCBX. And give them a click and just have a look. Support the sponsor if you can. Right, so let's crack on. So the first thing that we're going to do is we're going to import the SVG file that we created. We modeled a basic battery outline, which I then modeled what my circuit board outline was going to be and where I wanted my mounting points. Subsequently, I've 3D printed that component. I'm trying to get the light just right so you can see the indents, right? It's pretty close to the original. It's not completely perfect. So if I can trying to get that so you guys can see it well. There, oh, that's a good shot right there. Get the light just right. It is close enough that the light will receive this battery dummy, and the circuit board's going to go inside the final model for this. So, all right. So we're going to import the SVG file, and we do that by going to File, Import, and then Graphics. And then we get presented with this panel, and we're going to go to the File menu, and we're going to choose the board outline. Now we get to choose where this board outline ends up. Right, so we're going to put the board outline on the edge cuts. The edge cuts is the layer that the board manufacturing company knows is going to be cut out by the machine tools. Right, this is the final shape of the board. So we'll click on OK, and here is our edge cuts. Now we're going to clean this up because it's brought in some geometry from the file that we don't really want. So if I just double click, I can now start to select elements. If I can click and drag, I can now delete these lines. And then it's just this line at the bottom. Oh, don't want to do that. There we go. There we go. So that's our board outline. If I go into the 3D viewer, we now have a circuit board, which is currently unpopulated. So we're now going to take some time to bring in the components, place them, and then get this ready. Just fine tune it. And then we're going to run the wires. Yeah, we're going to actually run the copper tracks. Road Rally Race, yeah, it is pretty annoying when that happens. It was an artifact of how I outputted the SVG file. It's my own fault. But I'm currently working in a Libre, and my knowledge of a Libre 3D is developing. So I'm not as proficient in Atom 3D as I would like to be. And the only way that I can get better is by using it in projects and seeing problems and overcoming them. Right, so what we're going to do now is we're going to bring all of the components that we designed and had all the nice looking circuit diagrams, all of these components here, we're going to bring them into the board layout. Yeah, it can bring in loads of artifacts. Right, so we click this icon here, which is like a little schematic drawing with a little red arrow pointing to a circuit board. So it's going to import all of the changes, all of the elements that we've got in the schematic into the board tool. Or at least it should. Oh, it's having a think. I've got a funny feeling one of my hard drives has gone to sleep. There we go. Okay, we click the update PCB. And here are all of the components that we want. The first thing I'm going to do is I'm going to get the mounting holes placed. Because while these edge cuts are there and they show the holes, they're not really going to work well with the board manufacturer. You really want to define holes as a whole element, not an edge cut. So it needs to be a drill hole. That's what those are the words I was trying to string together. So what we're going to do is we're going to use these circles from the edge cuts that we brought in as reference material, so we can place the holes where we want them. So let's grab the hole and we hit M for move. We can zoom in, and I'm using the middle. I'm using the. Oh, we're upside down. I'm using the middle scroll wheel to zoom in and out, and then when I want to move things around, I'm pressing the middle mouse wheel and I'm dragging from left to right. So that's what's going on there. Right, so and what we're going to do is we're going to place this right on top of the hole and do the same for the other one. Like so. Okay. I'm going to move this. In fact, I'm going to delete the whole screen printing. We don't really need that because we already know it's a hole. So now I'm going to remove. See if I can just. I'm turning off these elements. I got to figure out which element I want to turn off to hide these holes. So these are masks. You see everything starting to disappear as I. Yeah, we're bang on with that one. We're bang on with that one. Oh, it's just slightly off with this one. Okay, we want the edge cuts because we're going to play with that in a second. Okay, let's just turn everything off, right? So just leave the edge cuts. That's all we've got. Why that's showing up like that, I'm not entirely sure, but never mind. So what I'm going to do now is I'm going to select the edge cut. And I'm going to attempt to select the circle. There we go. There we go. Right, I can turn everything back on now. And those edge cuts. Those edge cuts will now no longer exist for the holes, just the outline. That's all we want is the board outline. So when we go into 3D viewer, what should in theory happen is we'll see this board with the holes in it, but this time the whole component is making the hole. So let's have a look to see if that's, let's see if that's doing what it should do. This might display a bit weird, but we do have the holes where we want them. Perfect. Okay, so now it's time to place the components. So we're going to place the power jack first. And I'm going to put the power jack down here. And I'm going to rotate it so the 12 volt is on the right-hand side. And I'm just going to change my grid. My grid is a little bit too fine. So let's go... Let's put that right on the edge of the board, like so. So now I've got that, I want to place my microcontroller. And we're going to grab the microcontroller, and I want to put that at the top of the board. Now you'll notice there's a keep out zone. Yeah, you see that keep out zone just here. Now that keep out zone is for the antenna of the ESP8266. What we don't want is any copper to be in and around this area because it will interfere with the wireless performance. Now, if you go on the Expressive website, you can see a I want to say an infographic, but you can see some specifications around how you can mount this module. You can create cutouts. So you got like a slot in and around this area. You could do it so that the antenna section is overhanging the board. Here, we're not going to do that. We're just going to mount it flush with the board itself. Anyone tell me I should do this for a job? Do you mean the circuit board layout or do you mean streaming? Road Rally Race. Okay. So next up, we're going to grab our buttons. I'm just going to loosely... It won't be streaming. It won't be streaming. Thank you, Vex. That's confidence inspiring right there. So we're going to finesse this a little bit. So I'm going to grab my diodes. And I'm going to place them just off to the side. My LEDs. Streaming's not that bad. I mean, one thing I really like about streaming is the fact that I can interact with people live and I can take questions, help people. I like it. It's cool. Right, so I'm gonna just do a layup where the text here is just sandwiched slightly in between each of the buttons. Just to get my spacing, there's probably a better way of doing this, like using an array command. But I'm just going to grab each of these, and now I'm going to move the reference. So I select the reference, hit M, and I'm just going to drag this off to the side. So this is like some silkscreen like printing text. If I show you in the 3D viewer, you can see like the switch references, right? So the reason I'm moving this is because I'm going to be placing a component in here shortly. Okay. 1, 2, 3, 4, 5. We got 5 buttons here, but we don't need 5 buttons because this is only a 4-channel board. So why have we got 5 buttons? One of the buttons is a reset button. So this top button, switch number 1, if I'm not mistaken, is a reset button. So let's check our schematic and confirm that that is the case. So there we go. That's actually a neat thing to show you as well. You can select your component and you can navigate between things, and you'll notice that the button is selected. So let's say, for example, we're in our schematic and I want to work with where's the buttons? Where's the buttons? Buttons. There, right? I want to find out, well, where's button 4? So I select it, jump in here, and you'll notice that button 4 is actually selected. Even to the point you can go to your 3D viewer and button 4 is highlighted in green because we've got it selected. So it's a real nice way to kind of grab your components and see where they exist in real life. Okay. So there's that. We're going to grab button number 1 because button number 1, I'm going to actually pop button number 1. Where am I going to put button 1? Pop him out of the way a second. Now, it needs to be over here, connected here. So you could see these blue wires. These are called air wires. It's showing us the connections that the component has. So we're going to have to run proper traces to connect these pads together. So it makes sense for me to try and uncomplicate the wiring of these buttons. So I'm going to just move this like so, right? And then I think I'm going to put my programming port over here. So one of the things you may notice in this circuit design, the Wemos D1 Mini has an integrated USB connection. And we don't have that in our design. And there's a very good reason why I don't include the USB functionality on my microcontroller projects. The reason for that is component count. When we look at an ESP32 or a WeMOS D1 Mini. Let me just switch to the overhead. The components on here, the vast majority, there's like 2 components on here relating to power. The rest of the components on here are to do with USB functionality. And that takes up quite a bit of space. So what the intention here is that by removing the need to have USB functionality on the board, I don't need to have, I've got fewer components. It's easier to route the wires and circuit traces, and the overall cost of producing the board is reduced. Well, what about programming? Well, I've just showed you. You've got an ESP32, right? This little gray wire grounds the enable pin, and it turns this module off. So I can now talk to another module, be that an ESP32 or an ESP8266 or any other microcontroller for that matter. I can use this as a programming board. I've already got the hardware. So it makes more sense to do it that way than any other way. So it simplifies things. And what's the saying? Keep it simple, stupid. Right, I'm just going to tweak the position of this module. Now, the gradient of my grid is too coarse. So on one click of the grid, one snap of the grid, I'm a little bit too close to J3. And then when I go one snap left towards the hole, I crash the courtyard. The courtyard is a space that a component is given to allow it to exist on the board. So I need to change my grid fineness. So let's half the grid, and then I should have a little bit more resolution to adjust. I want to sneak up to there a little bit. Now, we're not actually going to populate a component here. Let me see. View. Have I got the component there? Yeah, so in this, you can see that there is a pin header. We're not installing a pin header. This is going to just be a through-hole plated component. So I'm going to actually remove this 3D model so that it represents what it's going to look like in the real world. So let's do that. So if I select the component, double click it, we get this footprint properties box pop up. And what I can do is I can go to the 3D model. Now, if I've got a footprint that doesn't have a 3D model available for it, what I can do is to model a step file and import it and combine it with my own components, right? So I can build my own components in CAD and get a 3D representation, which is brilliant for visualization, brilliant for modeling an enclosure. So I'm going to uncheck the show option, click OK. So when I go to the 3D viewer now, the component is not there. We've just got these plated holes. So we're going to put some text on the back later to make sure that we know which hole is 3 volt 3, which one's ground, which one's transmit, which one's receive. So it makes it easy to wire things up. So, right, okay, enough chatter. Let's get back to placing our components. So now we've got the core of a component. So I'm just going to nudge these buttons up. Looks about all right for me. Now I'm going to place my diodes. What I like to do is I take my diode and I actually click it in the center of the component I want to align it with. And then I move that and it should hopefully snap in line with it'll snap in line with the component I just aligned it with. Yeah, so we align the centers and then we can move it around. So let's do that for the remainder of the components. And we see here that the courtyard isn't, we've not got enough space. So let's make it a bit, make it enough space. Okay, cool. And now we're going to move these two buttons down. All right, so there we go. We've now got our buttons and LEDs aligned. With the enclosure, I'm going to make a little channel for the diode and the button. There'll be a little button press that'll make its way to the outside, to the top of the switch. And I'm going to make like a light tube that the LED will be able to shine on the outside of the enclosure. Right, let's just quickly take a look at that in 3D, make sure we're happy with what it's looking like. I think that's looking pretty snazzy. I like it. We may need to odds the text alignment, right? We may need to change the placement. In fact, I'm going to. I'm actually going to put it to the top left, and that way I can sneak in some components through the center of the board. So I'm constantly reevaluating where I'm placing things. Can I select all the text at once? I don't know if I can. It'd be good if I can. Oh, look at that. That's cool. I didn't know you could do that. You can select all the text in one go. Okay. Next up, we have got the output. So I think I want to place the output channels over here. And yeah, let's put this right up on the edge. And again, I'm not actually going to put a pin header in here. I'm going to... in fact, do I want to change the footprint? Yeah, I'm going to change the footprint on this. Because looking at this, especially if considering that these are going to be having 2 amps output, up to 2 amps output on each channel, we need to make sure that the trace thickness of these components is good enough. And I think that's not good enough. So let's switch back to our schematic and let's look at our output, J1. Let's go to our footprint assignment tool. That's just loading. Okay, so the 2-pin header is a solid wire, right? I think we should change 7.8 millimeters is the spacing of the pins. I think that's a little bit too big. So let's come down. Let's see if we can do a 4 millimeter. What are we? 8-pin. Oop. Solid wire. One by 4, 1 by 5. We need a 1 by 8. Six. Oh my word. Am I only going to find up to 6? Yeah, it looks that way. Well, that's irritating. One. What do we want? 1 by 0.8. 1x 0.8. Hey, Buck, welcome in. Right, okay. Well, we're scrolling through this section here to try and find a component. I don't want a pin header. Yeah, finding one that's going to be appropriate, right? This is a little bit of a guessing game, because what I'm interested in is the pads. That's all I'm interested in. Okay, I think we're going to go... All right, I tell you what. I'm going to leave the pin header as is. And I'm going to modify these pads to fit what I want. So we can actually modify the pads by double-clicking them. And we get some boxes here. So let's say, what if we move this to... So it's oval? Is that oval? 1.7 by 1.7. That's a circle. Okay, 1.1. Let's go 1.2. So you notice that pin is now much bigger. So let's rinse and repeat, right? So we're gonna go circular. Oh, cool. I can't remember what the settings were. What was it? 2 millimeters. Okay, cool. So let's go circular. 2 millimeters, and it was 1.2. I did say 1.2, didn't I? I did. Abadas, welcome in. How you doing? We are live streaming on YouTube and Twitch tonight. And we are coming to the conclusion of the circuit board design. This is the final live stream in the series. Live stream number 1, we did the prototyping. Live stream number 2, we did the schematic. This live stream, we are doing the board layup, ready for manufacturing. That's very kind of you to call me a KiCad master. I would prefer to call myself a KiCad user. And hopefully I can show some tips and tricks that I use. I'm not suggesting that these are best practice, because I'm not an expert, but I do use the tool quite a bit. Okay, so I'm just beefing up the connections because we're going to be running up to 2 amps. Twitches are better. Oh, you gotta start the debate. Gonna start the debate. Okay. So we've got a bunch of resistors now. Now I'm just going to align. And for some reason, my grid is not fine enough to do what I want to do. Why is it not doing that? That's gonna spark the debate, Vex. That's gonna. I mean, next you're gonna tell me you don't like Marmite. Here we go. I'm waiting for the implosion of the space-time continuum. Right, okay, so let's move these over here. Let's see if we can... I want to try and place these in a location that's going to make sense. I'm just moving them around to see what happens with the air wires, right? Okay, I think what I'm going to do is I'm going to take R1 and R2. And I'm going to place them over here. Let's just bump up my grid. My grid is too fine now. Okay. We're looking good, we're looking good. Now if I bring these in, and I pop them this side, I'll probably sneak them in on this side of the board. Like that. My only worry is that we could be penning in some of these components, but we can go two-sided, right? We can go a two-sided circuit board. Now I'm going to bring in my MOSFETs now. I'm going to pop my MOSFETs in just here, and you'll notice I've aligned these a particular way, right? I've aligned them alongside my buttons. I'm just going to sneak these a little bit. I just want to give a little bit of space in between them. Just so that if I want to put a heatsink in here, I have a little bit of wiggle room. It is going to be a little bit tight, but, you know, it is what it is. I'm just refining things a little bit because I've got some additional components I need to get in here. So let's grab our voltage regulator. So this is what's going to convert our 12 volts to 3.3 volts. Let's rotate it this way. So this faces the 3.3 of my microcontroller. Let's put it. Can I sneak it in here? Yeah, I think so. Now we're gonna have to do some cleanup work in a second. Oh, okay. Let's rotate. Just contemplating where these are going. Okay, cleanup is that the silk screen is kind of like clashing. It's a little bit tight on things. And now lastly, we need to put some fiducials in. Now, fiducials are essentially like these little dots that I can use for the Lumen pick and place machine that I'm in the process of building. We will be returning to the Lumen build in live streams starting next week. I will be building out the linear motion system of the Lumen, adding all the belts and getting the surfaces moving on their own. Well, I say on their own. They won't be powered because I don't have a motherboard yet. So yeah, it'll be pretty much everything that I need to make the Lumen move around. So Frank is coming, right? He's coming. He's needed. So we're going to put these fiducials in, and the fiducials are essentially like a little dot on the circuit board that the pick and place machine can optically locate, and it allows the machine to calibrate against where the circuit board has been placed on the bed of the pick and place machine, so it can accurately move from component to component and place them correct every single time. And it's recommended that you have a minimum of 3 fiducials. So this is the first time I have ever used fiducial. So this is just as much an experiment than anything else. Some people are spoiled. Well, I am building the pick and place machine myself from scratch. So okay, so let's have a look what this looks like in our 3D viewer. I mean, I'm not doing anything particularly special here, right? Okay. Can I sneak the fiducial in up here? Unfortunately not. The courtyard is not allowing me. Okay, so let's view this now. All right, so that is our board. I actually quite like that. So the idea is that the power comes in here. It supplies 3.3 volts via this voltage regulator to my microcontroller.
Thank you, Hustubin, for the follow. Hope you enjoy your stay here.
Hey, Husband, thank you for the follow. All right, so yeah, the voltage comes in through here. And when we either trigger an event by pressing one of these buttons, or if we send a Home Assistant command, it will... Someone's trying to get me. What's up? What's up? Buck. Are my sound effects coming through? Because I heard that. Double audio? Ah, right. Double Welsh. I see. That should have gone away. So there's a couple of things that I need to clean up on here. So obvious things is like my screen printing is a little bit overlapped and some of it's like missing off the board. So let's get rid of this pin header. We don't want this pin header because we'll solder directly to the board. Okay, just uncheck the show, click OK, and now let's go back to the 3D viewer. And there it is, right? I may thicken these up further. I may make these bigger again. Just out of interest, did my stream alert and voice come through on stream announcing the follow event? For those of you who are watching on YouTube, these are events that are coming in through the Twitch portal. Oh, nice. Thanks, Abatus. Cool. All right. So what we're going to do now is we are going to just tweak the silk screen or screen printing bits for these components. So let's move the J2 onto the board. The system will complain about this, right? Quite a bit. So let's just pop that in the center. And we'll move the switch reference. And we'll pop that just there. Now I'll probably put my logo on here as well, but I won't do that on stream. It would be to add like graphics and logos to a board. All you do is you have like an SVG file or a DXF file that you want to include. You go to File, Import Graphics, and you just choose the layer that you want to bring it in on. Now, bearing in mind when you bring it in the first time, it will be on it. It'll be correct from looking from above. So, for example, if you put this, say, for example, you want your logo on the bottom of the board, you bring it in on the bottom silk screen. When you look at it in KiCad, it will be reversed. So what you need to do is bring it in on the top silk screen and press F to flip it. And by flipping it, it'll reverse it and place it on the bottom of the board. So there's a little hack there. Right, so now comes the illustrious task of trying to wire these circuit traces and make sure we don't miss anything. Now, one of the things I'm going to do is I'm going to use what's called an auto router. I could spend time trying to wire this by hand, But if I can get the auto router to complete the majority of this task for me, then it's going to save me a lot of time, and then I can just pick up anything that it can't do by hand. So it's like minimal by hand bits of work. This is your favorite part of the game. Yeah, it's a little bit like playing like Snake on the Nokia 3310, right? You click on your line tool and you literally say, right, where's this gonna go? It's gonna go here. It's gonna go all the way along here, and we're gonna sneak it through here, and then we're gonna apply it there, right? So you've got a trace, but you know that's not particularly aesthetically pleasing. So let's use the auto router. I've got the auto router plugin called Free Routing installed in KiCad. For anyone interested, I'm using KiCad 7. I believe the latest version is KiCad 8. Now, the auto router has decided to jump onto another screen. So let me just bring that in. So here's the auto router. And what we can do, if you got the board reference, if I just say, let's have a look. I'm going to keep everything default, right? And I'm going to hit the start auto router option. And now it's going to go through computational operations to try and connect all of the tracks to where they need to go. If you can spot the first flaw in this process, I'll give you a shout out in chat. What's the problem? Okay, the auto router is completed. How does it know, for those who are not familiar? So when we first started, you saw those little like wires connecting point to point. So those are called air wires, and essentially it's what's known as a rat's nest. It's literally Steve's the problem. Oh, thanks, Road Rally Race. That's not, you got a shout out for that, right? But that's not the answer. Yeah. Ultimately, right, it's trying to make the connection from one location to the other based upon the design parameters. So, for example, you've got the courtyards around components. You've got courtyards around pads. You've got through holes that this is trying to navigate. Equally, if it's going to go around corners, how does it do the like traces? Does it do straight, like right angles? Or does it do a 45 degree angles? Effectively allow... it's bad practice to have right angles in your traces. I believe it can cause the circuit to heat up. I'm not sure if it's like some collision taking place in, you know, the atomic level physics as it's trying to do like a right turn at 90 degrees. So the 45 is a little, to be honest, while that may be true if you're working on ultra high speed circuits like, you know, HDMI signals and super high powered circuits and stuff like that, that's not where we're at in this journey, right? So you can get away with right angle turns in your circuit traces. It's best to avoid them if you can, because when you get further down your circuit design journey, you've got fewer bad habits to try and train out. Anyway, that aside, there is a problem with this circuit. So I'm going to run there's a design rules check here. And this looks for problems in your circuit. So we'll run the design rules check. and it looks for problems like things not being routed properly, you know, unconnected items. Here you go, we got clearance violations on certain things. It's not happy, right? So you've got errors and warnings. Warnings you don't have to worry too much about. So warnings is like, what is it? Warning, footprint header 1x4, copy, something to do with the library version. Oh, what was that header there? What was the pop-up? I can't get it to come back up now. So we got a silk screen overlap. Right, so it's just these are more like yellows. They're yellow warnings. They're not showstoppers. We've got 6 errors though. So we're violating the rules of the design, saying that we got pad clearance problems. So let's see. That could become a serious problem when it comes to board manufacture, because your manufacturing company like PCBX may not be able to manufacture things to the tolerances that you're trying to design to. So it's always worthwhile looking at your board manufacturer's website for information about their capabilities and making sure that your EDA software is configured to match that, so you're not fighting your board manufacturer. Okay, so we've got problems, but the problems that are shown here are not the problems that we really need to worry about. Can anyone remember how many amps we said we were going to allow or rate this up to? Can anyone remember? Eight. Total, yes. It was 2 amps per channel. Right? So each one of these channel outputs allegedly can do 2 amps. Do we really want to put 2 amps of current down a trace this big? That is probably not recommended. That's more likely to become a fuse. Yep, it's 2 amps per channel. So, if I remember correctly, I would need a trace width of about 1.2 millimeters in order to account for that amount of current that we're going to pull. So, the trace width on this, let's have a look at the trace width. 0.25. Yeah, that ain't gonna cut it. Okay? So we're gonna have to go through this process again. Sil, welcome in. Thank you so much for that resub. 52 months resub on Twitch. Let that sink in for a moment. 52 months. Wow. Thank you so much, Sil. Appreciate you. Tonight we're live streaming on Twitch and YouTube. So for the YouTube viewers watching, that's what you just saw was an alert from Twitch of somebody subscribing to the channel. Okay, let's cancel. So let's get rid of all of our traces. How are you doing, Sil? Hope your evening's doing well. Yeah, I know. That's disabled at the moment. That will be coming back. That will be coming back. My inner monologue is coming back. I need to make sure I get the moderation set up on that right. Yeah, I need to get my channel point rewards also sorted out as well. So, right, we're going to get rid of all of these traces. Let's do that now. So we go to Edit, Global Deletions, and we get this little menu pop up. And we can say tracks and vias, click on OK. Yes, I'm sure. And they're all gone. Right, so we're going to start playing with net classes. You're all right. You're 1 of 10 way on the populated Amiga 4000 motherboard. Nice. Nice. Okay, let's move that out the way. Okay. So we're going to play with net classes. Now, net classes is each of the traces is called a net or network, I suppose that's an abbreviation for. The classes side of it is you can actually define properties of the net classes. So let's have a quick look at what these net classes look like. So if we go to net classes, I'm going to add a net class called power. And I want my circuit traces to have a 1.3 millimeter thickness. So we're going to go slightly above. There's so much through-hole, I bet. Through-hole stuff is tough, right? Okay, so now we've got the net class. I'm just going to quickly save, and I'm going to jump over to my schematic. What I'm going to do is I'm going to come to these power flags. Like so. And I'm going to select it, and I don't know if you can see because of me being in the way. Let me just duck. Can I duck out the way? How do I do this? How do I do this? Can you see just down here that the resolve net classes is currently set to default? Well, we're going to change that, right? If I just double click this line, okay then, cancel. How do I get the net classes? Right click, assign net class. There we go. We assign either a power or a default. So we're going to choose power, click on OK, and then we select the ground. We also right-click, assign net class, and make sure that's assigned power. Okay. And we save this. Let's go back to our schematic, and we're going to click this button again because we made some changes in the schematic. Anytime you make changes in your schematic, you need to come in here and click this button so it pulls all of those changes into the board layout. So we're going to click on that. We're going to just click Update PCB and then close. And we're done, right? Let's run the auto router again this time and see what the difference is. Okay. So let's hit the auto router. How long, Sil, until you get your Amiga 4000 motherboard completed? How long do you think it's going to take? In 3, 2, 1, start auto router. Okay, so we can immediately see that we've got thicker traces going on. Okay, it's complete, but I can see an air wire, right, between this ground line here and this ground just here. So we've actually got this ground pad penned in. So we need to figure out how we can fix that. I've got an idea. But before we do that, let's see whether or not the design rule check picks up that this ground pad is not connected. It should. Let's try it out. Run. Okay, we got 5 errors. We've got unconnected items. So we go up here. And it's telling us that the ground pad is not connected to the ground line. So let's fix that before we go any further. So it's not really that painful. It's big parts, so it fills up quick. But still. Yeah, right. But add it to the ZIF sockets, ROM chips, some of the chipsets. Put myself together about 1 to 2 hours on it twice a week. So maybe close to the summer. Can consider getting the CPU board for it. Nice. So, Sil, just for those who don't know, what are you building in chat? If you can let people in chat know what you're building. So what I'm going to do, I'm going to grab this. I'm going to grab this here, this trace, and I'm going to just drag it. And I'm going to make a little pocket. Don't particularly want that to be like a right angle, because we already mentioned earlier about right angles. So let's not do a right angle. Well, that looks horrible. What on earth is that? My grid is not fine enough to do that justice. Here we go. Oh, let's see if I can just tweak this a little bit to get it. Do you know what? I'm going to delete that completely and I'm going to try again because that just looked horrible. So you're building an Amiga 84000 Red B motherboard. Is that right, Sil? My grid is still not fine enough. Okay, let's change my grid reference. What are we? That's 255. Let's go 1 down again. So I'm just adjusting my grid because otherwise it looks terrible. There we go. So we've created this little pocket that I can now just draw a trace out. I see what's going on here. So it's trying to draw a ground wire, which is way bigger than it can be, right? It's trying to draw one this big. Okay, so let us edit predefined values. So I'm going to put in some 0.25, 0.5, 0.75, 1.3. Okay. So now I can override the net class and I can choose my own trace width, but I'm intentionally doing that. So I can now draw like this little line here, right? Grab a via. A via is essentially a little component that I can use to bridge the board, right, from one side to the other. So we'll pop a little via just by here, a little via by here, and then we're just going to do a ground wire. Let's switch to the bottom side and take it to there. And that's where we need to be. Right, so we have a bit of a problem in that this ground wire This is problematic. It's encroaching on this fiducial. You can see these red arrows that's telling us that we've got a problem. So what I'm going to do is I'm going to delete the ground. And we're going to fix this another way. So what we're going to do is I'm going to create a fill zone. So let's create a fill zone on the bottom side of this board for ground, right? So we select the fill zone. Let's choose the bottom and now let's find ground. Click OK. And now we've got a polygon tool, right? So we can come in here and we can draw a chunky ground fill. Take it all the way up to here. Bring it all the way down. Okay. Now, when I do the design rules check now, it's going to fill that area with copper. And it will be blue. So all of this blue area that we see here is ground. So what I can now do is I can go to the top layer. I can use a wire from this ground and just go down. And this ground wire doesn't need to be like massive, simply because it's driving, it just needs to have the current for the microcontroller. It's not driving the current coming out of the MOSFETs, the power MOSFETs. So I just grab a fiducial, not a fiducial, a via, click that, and that is now grounded. I can do exactly the same here in between these two ground pins, and they're now grounded. And the cool thing is that these components are actually tied together, and they are filling up the power side of it, the 12-volt side of it. Okay. Now I also see a problem. Ah, no, I found another problem. The nets for these channels, they've not updated. Well, that's annoying. What a predicament. So what we're going to do is, let's go back to our schematic. And we're going to update these channel wires, right? We're going to say that these channel wires are power. Because it's more than just giving it a ground. It's going to be pulling current, I would imagine. So we click power on each of these channel net class assignments. Hit save. Back into the board. Click on update the board. Okay, but you'll notice that these traces haven't updated. So I think we need to come through here. Let's see. I'm going to try something. I may have to tear up the. I may have to tear up all of these copper traces, but we'll see. We're going to try it where we just remove the channel wirings. No, we're going to have to do more than that. Yeah, we're going to have to do more. So let's do this. Let us rip up the traces, edit, global deletions, tracks and beers, click OK. Right, so we wipe everything out. I'm going to do another fill zone. But this time we're going to do it for 12 volts. And it's going to be 12 volts for the output. So there's going to be plenty of copper supporting the output power requirements. Let's see, 12 volts on the top. So this is going to turn red when we get going here, right? Okay. Let's do a design rules check. Okay, so we now got this copper. These fill zones, I'm not... Do you know what? I don't like these thermal reliefs. I think that's going to impact the ability to put current through this. It's going to make it a bit of a nightmare to solder, because these copper fill areas, what they will do is they will wick away the heat into those copper zones when you're trying to solder wires. But with the only other thing I could do is possibly see if I can make the thermal relief a little bit thicker. But are we kind of... Let's have a look. Thermal relief gap 0.5. Thermal spoke width 0.5. Let's make that 1.3. Because that's the requirement for us, yeah? Run DRC, it'll redo the fill. Close. That's more like it. I can live with that. Let's do 1.3 on the spoke width. 1.3. And there's 4 spokes, right? So that's 3, 6, that's 12 amps that we can potentially pull through the pad if we've got all 4 spokes. So that's good. Run the DRC. Close. Now, if I do a view the board, you'll see these copper fills. Can you guys make that out? You can see the copper fill area. So that's pretty cool. Liking that a lot. All right. Let's see if the auto router can hook everything up. Because if it can't, we're going to have to think again. Right, here goes nothing. And the cool thing about the auto router is it gives us the ability to iterate through a couple of different circuit designs. Yeah. This is interesting to see this like go. Okay, so I can see that we've got a couple of unconnected items that we're going to have to fix. Let's see what we've got. Let's run the DRC. We've got 2 unconnected items. So we've got... We've got the ground. So this ground pad is not connected. I can see a possible way of fixing that. I think we might be able to sort that out. It's going to be a bit tricky, but we'll sort it. Okay, and then we've got 12 volts. So this 12 volt line is not connected to 12 volts. and we're on top of the fiducial, so we gotta fix that. We can't have the fiducial compromised because there'll be errors. All right, let's see if we can work the problem. Now, there's a couple of ways that we can try and work the problem. And tell you what the first way we're going to try and work the problem is I'm going to delete my fill areas. That's the first thing. And we're going to run the auto router again. Edit, global deletions, tracks and beers, go. Yeah. Right, let's go again with the auto router now without the polygons in place. It did give me a warning about that. Minimize you. Let's bring you. Okay, let's run the auto router and see what this does. This should be a drinking game. Every time someone says, fiducial, drink! Right. Okay, so I've spotted at least one air wire. So it's a ground. Okay, so our channels are good. So we've got a ground fill. We've got to bridge these 2 points. Okay, let's do a DRC check. Yeah, one unconnected item, and we've got these fiducial that are currently being obstructed by this ground. So what can we do? Can we move the fiducial? Not really. There's not much. Not much in the way of space here for me to move the fiducial. Unless we make some room. Like that. Okay, that fixes the fiducial problem. We no longer have an error there. But what we've got is an isolated ground on our power regulator, which needs to be resolved. So we got this big, thick, chunky ground plane wire here, which needs to be connected to this pad right here. Let's bring the copper to the top, right? So there we go. We got to get this connected. So how on earth are we going to do that? I think I've spotted a way of doing this. So if I drag this line this way, we're going to create a pocket. I'm also going to drag this line and this line. In fact, let's get rid of these lines a moment. These traces. And what we're going to do now is we're going to put a trace in. And let's use our Usenet classes so we get the right. In fact, let's put our via in there first. Less than ideal. What I want to do is to create a pocket for us to put another via. That's not going to work. Okay. Let me sort out this ground via first, right? So if I go 0.5, let's bring that out to there. We'll pop a via on there like that. Oh, it won't let me. Okay, can I bring you... Okay, that's kind of working out. Rhubarb, question for me. Wait, shoot. What? Give me a question. Ask away. Which is the input? What do you mean? What does baffled mean? Okay, let's stick a via on the end of that. Like that, right? And now I can flip over to the rear side of the board and run a ground wire to there. Put a via on there. And now we've got a ground wire, right? What we don't currently have is 12 volts on pins 1 and 3 of not the output. Yeah, that well, yeah, that did. Oh my word. Man. Okay. So I just spotted something which looks a bit rubbish, right? I'm gonna fix it right now. These 12 volt, the 12 volt line here is absolutely puny. So let's fix that with a ground plane. Let's put in a fill. Top and 12 volts. Click OK. Oh, actually no. Top. Oh yeah, it was right. It was right. Perfect. Okay, so let's go. And I just want to encompass this area inside like a 12 volt plane. All right, let's do a design rules check to fill the plane in. And now we've got a decent amount of copper coming up in and around our 12 volt rails, right? Almost to the point where we can get rid of these wires because the fill plane is doing a good job. Right, so let's get rid of these. We don't want them. They are surplus to requirement. All right, cool. So now we've got a decent amount of copper up here that we can try and get 12 volts from to power our power shower. No, our... Why did I found that way funnier than I should have. Right. Oh man, it's total squirrel moment, right? So we got to get 12 volts in here. We're only going to be pulling like a couple of milliamps. A couple of hundred milliamps is all we're going to be pulling off this voltage regulator. So it's not a big deal. And I'm trying to figure a way of getting myself out of this rat's nest of wires. So if I can bring a 12 volt line through this, you know, between this fiducial and get it in here, that will probably work for me. That could work out really well, actually, thinking about it. I'm just looking at an alternate route, just trying to figure out where we can go. So let's put a via on. Let's put a via on here. That's a 12 volt via. And then we're going to... You're evil, Rhubarb. You're evil. That's funny, but evil. Okay, this ground wire needs to be moved. Right, let's see if I can sneak this. Let's see if I can sneak this in. Right, so if I place that, if I place that here, right, and then do a oh no, no, look, I'm penned in. I'm penned in. Ah no, have I? What have I done? Okay, so pin 1 and pin 3. One of them's the input of the power regulator. One is the enabler. Right? So it needs to be connected. So how on earth am I going to get this in here? Oh, man. Seriously? Okay, I've had an idea. I've had an idea. Okay. So if I place a via here, can I get a via there? And one there? I don't think I can. That's too tight. It's too tight. It can't be done, Captain. Right, okay. Can I... Oh, Steve, you're a doofus. I'm being blind. Why don't I just bring this wire up to there, and then I don't have a problem? Like, don't. I could probably go. I could probably do like two. So this is a 2-layer board. I could do a 3 or a 4-layer board, but I'm challenging myself to do this in 2 layers. Okay, so have I now rescued myself? I think I might have. So if I go to the top copper layer, bring it to this point here, just delete that, and we're gonna stick a via on there. Oh, like that, like a glove. Stick one there too. Right, and now I can connect this to that. Let's give it a little bit more trace width than that, right? Bosh, like so. And now let's flip over to the bottom side of the board. All right, I've just spotted a stupid situation. Yeah, I'm gonna get rid of that. It's all right. I'm problem solving on the fly, and I'm finding it. Right, exactly. And it challenges me to try and get things to work in a particular way, right? So I'm going to bring this trace down here, and I'm going to put it on there. Like that. And now I'm going to drop a via on there, like that. Okay, and we're now connected. I can hopefully now place a via here. And then run a ground wire over on the bottom side. Oh my word, this is getting complicated. We're going to use net class. Flip over the bottom side. Yay! We did it. We did it. Okay. Let's just quickly do a design rules check. Okay, so we've got one error. So we got thermal relief connection to zone, incomplete zone, minimum stroke count to actual 1. So let's have a look. Okay, so that's probably more to do with the fact that this pin is square, right? So I think what I'm going to do is I'm going to change this pin. I'm going to change it to circular. And then let's do a design rules check again. All errors gone. Yes. All errors gone. We just got a couple of warnings. Let's have a look at what the warnings are. Warning, footprint pin header is different. I'm guessing that's different to the one in the library, is it? Does not match the copy in library. It's because we modified it. We turned off the 3D model. That's all that is. So we can ignore that one. We can ignore that one. We got a silk screen overlap on reference D3. Right, so this is our diodes. D3 and D4. What do we do with our other diodes? Ah, right. Okay, so let's... I see what's going on here. So let's go to our LED D4. We're going to move the reference. I move it. How can I select the numbers? Selecting the switch. No, come on. Give me a break. Throw me a bone. Let's get rid of the traces. Would that help? Yes. All right, we'll pop switch 5. We'll put D4 here. Being problematic to select it. Normally, it gives you like an option to select. Can you test the board in the software? No. I mean, right? Okay, that's not strictly true. Can I test this the board in this software? I can test the board, but not in the way that you mean. So I'll tell you what I'm going to do. I'm going to have to move the switch to get access to the reference, and now I can bring this back in. Have I done it right? Oh, dang it. I asked for a bone. Right. So yeah, you can test the board, but it tests it electronically based upon your schematic and the design rules. If you wanted to test whether or not it would do the switching and stuff, you can use software like Tinkercad. So Tinkercad gives you like Arduino components that you can drop into a virtual space. You can put a program on it and it emulates what the microcontroller would do. What I have noticed is, I'm not sure what boards are supported in Tinkercad. The Arduino Uno is definitely in there, but it's not particularly fast emulation. So for anything complicated, so let's say, for example, you wanted to use NeoPixel LEDs, that's actually pretty complex, right? So let me see if I can turn off some stuff to allow me to grab. There we go. Now it's starting to play nice. So what I did here was to turn off some of the objects in the viewport. And that enabled me then to see what I was, or let the software know I was clicking on a particular item. Right, let's switch everything back on. I think we're pretty much there. What's left to do? Let's quickly do a design rules check to make sure I haven't nudged components out of place. We now have 2 warnings. The 2 warnings represent the footprint library. It's because we turned off the 3D model, which is fine. I'm not really worried too much about that. But this is our circuit board. Let's have a look at it in 3D. So what is left to do here? Well, not a huge amount. If we want to put some graphics on the board, which I'm going to do, I'm going to put my logo in here. I'm going to put that on the bottom of the board. But other than that, there isn't anything left to do in terms of designing the board. We might want to, tell you what, I will tweak that C1 placement. And let's pop it this side of the component. And there you go, it's updated. Boss. Lovely jubbly. Right. So there is our board. This is a 4-channel 12-volt. Double check it. Well, I can double check it by hitting the design rules check, right? So the design rules check makes sure that the components are physically connected. You'll see here, unconnected items, 0. Right, we have nothing unconnected. All of our pins are connected. Each component is connected to their respective pins as per our schematic here, right? Everything is as we want it. There are no errors. There are only 2 warnings. There are some tests that have been ignored. Footprints that have no courtyard defined. That's fine. Add a QR code and link to your website. Hey, that's not a bad shout. Through hole in courtyards. Footprint component type doesn't match footprint pads. Not really worried about those types of things in this, right? It may be relevant in a more complex project, but for now, for this, is fine. So all that's left for us to do is to output the files ready for manufacturing. And to do that, we go to, first going to save. We're going to save the file. To output the files, we go to File, Fabrication Output, and Gerbers. And here we have the ability to configure what layers we're going to output. So F.cu is the top copper. BCU is the bottom copper. So we definitely need those. F and B paste. That's, let me see. That's possibly not needed. It's for like, for applying solder paste. Maybe if you're going to, I'll have to double check. You need to double check your manufacturer's website. They typically have screenshots of what you need to be able to output your file in the appropriate format. So we definitely need edge cuts. We definitely need the mask. We definitely need... I don't think we need the paste. So mask is for solder mask to be applied. Definitely have solder mask applied. Don't have boards that don't have that. Now you might have some like user-defined items for layers 3 and 4, but for right now, that's all we need. We need to specify where this is going to go. So we'll create a folder called Gerber. We don't need to plot footprint values or designators, I don't think. But again, check your manufacturer's website. Check the fill zones. We don't need a Gerber job file. Subtract solder mask from silkscreen. So then, yeah. Perfect. And then we click on plot. And that generates a bunch of files here. Now you need to generate your drill files. These are if you have through-hole components. Yeah, it automatically, KiCad automatically does backups for you. So we create an Exelon file. Usually Gerber X2. Absolute positioning. Generate drill files. And now that's the drill files created. And it's always useful to generate a map file. That helps the manufacturer overlay everything, and it gives them a visual reference of all of the hole sizes that if you are drilling through, that the component needs. And that will then flag up any issues. If you're trying to use a non-standard drill bit that they don't carry, they're probably going to reach out to you and say, hey, no, we don't do that. If you need a revision, there may be a handling charge to correct it, but always check your board manufacturer specifications to make sure you are submitting a file that your manufacturer has the capability of making. Any errors or any mismatches is going to result in additional fees for you to bear the cost of to correct things. So get it right before you send it off. Once you've done all that, typically you go into this Gerber folder. Go into this Gerber folder, and you see all the files. And all you do is you select all of the files, right-click, send to compressed zip folder, call it whatever you want, 12-volt control, right? And that is the file that you upload to your board manufacturer. So that is the end-to-end of making a circuit board from scratch for your projects. Live stream number 1 covered off the prototyping of the board, which we did using proto board and some components to mock up what we want to try and achieve. Stream number 2, that was where we did our schematic layout. And we designed our circuit in a diagram. And then finally, tonight's live stream was to make the circuit board and also to view it, prepare it for manufacture. Now, if you want to build an enclosure for this, one of the things that you can actually do is to export your board into what's called a step file. Yes, Mark. About us missed it. Let me scroll back and check. What did he say? Well, if you want to see the end-to-end process, if you want to head over to YouTube /IQ Workshop, you can find in my live stream section part 1, 2, and 3 of this project. So yeah, all available, right, for your live streaming or replay pleasures. So yeah, we've got this this board ready. If I wanted to model an enclosure for the board, what we can actually do is go to File and Export, and export as a step file. Essentially, that makes a 3D. It outputs the 3D model of your board that you can bring into a CAD program and then start modeling all around it. So yes, last things that I'm going to be doing is adding a logo, as you say there, Buck. I need to add a logo to the board, possibly a QR code and links to the website. That idea, I'm potentially going to use that. I like that. And then it's a case of just double checking everything before sending everything out to the board manufacturer. And in this instance, the board is going to be made by a company called PCBX. PCBX is sponsoring this live stream. I'm just bringing up their website. So if you want to check out PCBX, there is links in the description of the YouTube video and also in the About section of my Twitch live stream. PCBX is a board manufacturing company, which the unique selling point for this company is you do not need any EDA software to design your circuits in like KiCad. If you're just starting out and you just want to dip your toes into making circuit boards, you can use the online editor, at which point that gives you the ability to, let me see, what do we got here? We can design the sketch. We can do the PCB outlines. We can look at this in 3D. And then you can place the order all directly from the browser. PCBX also cover an assembly service. They have various different ISO products available. Tons and tons and tons of different permutations that should easily cover your manufacturing and project needs, including them actually putting the board together for you. EDA, E Echo Delta Alpha. But you knew this, right? You're just mocking me. I will be completely open book about what this will be. Yeah, I'll put that in the Discord. So if you want to join our Discord, let me see if I can trigger my Twitch bot to chat out to everybody. Oh, thank you very much, Buck. Appreciate that. If you want to join the Discord, feel free to come along. We're an inclusive community that is sole purpose is to help people start their projects, progress their projects, and finish their projects. That's something I'm very guilty of, is not finishing my projects. So that's going to be a different story in 2024. Sure thing. So I know that this is a 2-layer board. The board width is approximately 40 millimeters across. 40 millimeters by, what was it? You're asking me questions like that off the top of my head. Should we find out? Yeah, let's find that out. Yeah, it's typically the shipping that's gonna get you, right? So let's find out the dimensions of my board. Just loading up the model that I've made. And then we'll just do some measurements in that model. Okay, so there's the model. Let's find the sketch that we're interested in. That's the sketch. So let's edit that sketch. Okay, so if I just put some dimensions in between, this is going to over constrain things, right? It's going to complain, but I can get the values, right? So 66.5 millimeters. Oh, there we go. 30.3 by 66.5. So let's actually look at how much these boards would cost. 33.5. That's right. Is it not? 30.3. Duh. 30.3 by 66.5. Now, most board manufacturers have a minimum quantity of 5 boards. And let's get the quote. So, excluding shipping, which, depending on where you are in the world, is going to vary, right? Equally, if you're looking at trying to get board to you quicker, or if you can wait a little bit, your shipping costs are going to vary based upon that parameter as well. So you have various different options to your boards, right? So do you have a single, or are you making a panel? It could very well be I'm going to be ordering panels of these boards so that I can load them up into my Lumen PMP when it's finished and auto-populate these things. You can change the layer, the thickness of your boards, how many layers. So if we were going for a 4-layer board, it's still $2 for a 4-layer board, right? So we can change the surface finish. We can also look at what color we want the boards to be. So there may be additional costs for different colors. Let's have a look. No, it's still $2. Testing it fully. Your boards get fully tested. Delivery method. Additional options. Ooh, I tell you what we might want. We might want a... When we order a stencil. Can anyone see a stencil in here? It costs you $20 to ship from Adafruit in New York, but overseas is normally cheaper. Yeah. Right, let's have a look. I'm looking for a stencil. Part number, material, layers, thickness, board type, board size, lead time, surface finish, outer copper, solder mask, silk screen, testing, delivery method. Inspection standard, UL marking, okay, date code, healable solder mask, impedance control, gold fingers, right, edge plating, V-scoring, captain tape, press fit holes, via impad. Okay. So one thing I'm not spotting here is a stencil. So I will reach out to PCBX because I'm likely to require a stencil because I'm going to be using solder paste. So that's ultimately what I'm going to be doing. But depending, laser stencil. Did I just miss it? Did I miss it? Where is it? Additional options. I'm being completely blind. Under additional options, inspection standard, UL marking, date code marking, peelable solder marks, none. Right, impedance control, gold fingers. Okay. I will have to ask them. Let me try that again. 30.3 by 66.5. 5 boards, quote. Okay, I'm not going to do anything, right? I'm not going to click nothing. Additional options. Is it a checkbox? But I don't see it. Ah, okay. Here we go then. 30.3. 66.5. Ah, it was on mil, not millimeters. Let me redo the process. See, I'm learning too, right? So, what we want? What we want? We want quote, don't we? Get started. No, that's not what we want. Where the heck was the quote? PCB. Ah, I was on assembly. What a doofus. What a doofus. Right, that's why. Because they were going to assemble the board for me. So 30.3, 66.5, quantity 5 boards, get a quote. So yeah, I went to I was in assembly. That's where I was. So let me try again. If I go to black, white, single board, laser stencil, slider. Okay, go for the non-framework. Laser stencil. Right, so this is going to cost me $12, right, for 5 boards. It's going to cost me $45 total for the boards and shipping. Good job, I got my Twitch chat, right? Where would I be without the community? Where would I be without the community? Stuck. Sweet. Right, okay. So that's what I'm looking at. $45 for 5 boards. So we're looking at about $12 a board with the shipping. Which it says there a lot. No, just kidding. And we can change this, right? If we go Mail Express or Priority Express. I mean, you can adjust that. FedEx is pretty pricey. So let's go Mail Express. Apply. $19, $19, right? I know what I did there. 45, 43, plus is plus, right? It's not total. Duh. But, yeah. Right? Not too bad at all. I don't know how long Mail Express takes to come, but if you're anything like me, you're quite happy to wait for your stuff to turn up, and then we can go from there, right? Plan in advance. You're quite happy for it to take the slow boat to get to you. Right then, guys, I'm going to wrap up the stream. Thank you so much for hanging out. If you're watching on YouTube, made it this far, feel free to hit that subscribe button and give it the old thumbs up. That'll help the channel quite a bit. The next video you will see on this board will be an explainer video on the process and the final product and get it in use. Oh yes, Buck, you've got it right there. You've got to like it as well. If you're on Twitch, if you hit that follow button, follows are free. So all of the support that you guys give me, it is greatly appreciated. Thank you so much for hanging out. And I will catch you guys in the next stream. Until then, have fun, be safe, and I'll see you soon. Bye for now.